Welcome to the lecture series on convolutional neural networks. This video covers modern convolutional networks and some application on image recognition tasks and image recognition challenges. So here's a recent example, an image, and it's annotated, well, on this image is a person. It's in the yellow frame. On this image also is a hammer. It's in the red frame. And yeah, there's also a flower pot in the green frame and a power drill in the bluish drill. This is amazing. This is a multi-object recognition task. No, it does not say, this annotation does not say that the person is currently using the hammer, preparing for a blow. But the algorithm finds 4 different frames for 4 different objects in a rather cluttered scene. This is the example of a very recent ImageNet challenge. The more classical ImageNet challenge was to recognize one object shown on the image, and in total there were 1,000 different categories, 1,000 different potential objects. Many of these were in fact breeds of dogs or cats, so some of it was very specialized knowledge. In total there was more than 1 million of images in a training set, 50,000 images in a validation set, and 100,000 set aside for a test set. And this is how performance evolved over the years. So in 2010, which was the competition's first year, no team was below 25% wrong. Now, look a few years later, in 2017, 29 out of the 38 teams had less than 5% wrong. A really amazing progress, and that was achieved by the switch of standard computer vision tools to computer vision image recognition with convolutional neural networks simulated on big computers with lots and lots and lots of data. And here's the winner of the ImageNet Challenge 2012. It's the famous AlexNet. It has several convolutional layers. Here's a first convolutional layer, second, third, fourth convolutional layer. And then this is followed by 2 layers that are fully connected until finally it's classified in these 1,000 different potential objects. Now, the convolutional layers take 90% of the computation time. So this is really where the heavy computation takes place. Let's look at one of these layers here, the first convolutional layer, depth 48, and then it's 55 times 55. So inside this volume, there are more than 100,000 units. Then there's a second stream up here, the image representation with 2 different streams corresponds to 2 different GPUs that only talk to each other at a very few stages. So in the AlexNet, it was the designer who made the decision how many convolutional layers we have. And the question then is, well, can we make the data decide how many layers there are? And the idea is now that we have skip connections that make a direct connection from layer n to layer n plus 2. And here are weights. And now you can imagine that we set all these weights to 0. And then there is not this extra transform f of x. It's just a direct copy from layer n to layer n plus 2. So there's no extra layer. On the other hand, if not all of these weights are 0, if not all of the ReLUs are below threshold, then some extra transformation takes place, and this extra transformation is the function f of x. Let's look at this in a little bit more detail. So I have here the output in layer n+2, and say I look at the activity, the output of a neuron in layer n+2, and this is the neuron with index I. Then this neuron has some ReLU nonlinearity denoted by a G here, and it gets direct input from this neuron in layer n with the same index, and then it also gets the input via this function f of x, and it gets the component I of this function f of x, and this is a function of the whole vector in layer n. Now, what is this function f of x? We have weights here, w, so this is sum over j wij in layer n+2. Then we get the nonlinearity here, which is g of, and then we get the layers here in layer n+1, which is w sum over k, jk, layer n+1, xk of layer n. And now you see what I already said, that if all these weights are 0, then f does not contribute. And then we just have the shortcut. Now, why is this useful? Well, I already said that it's the data now that can decide whether we have the extra layer represented by this function f of x or whether we skip it. Now, just training very, very deep networks also has the standard problems of vanishing gradient, a bias problem, a sort of all the different problems that we discussed in the context of backpropagation. And therefore, training a deep network with hundreds of layers is super, super slow, or people say it doesn't really work as well. Now, what I would like to show here is that if we take the derivative, if we look at the gradient, then there's always this line here, which guarantees a full transmission of the information from the output towards the lower layers. So let's look at this dxi in layer n+2 with respect to xk, a component k in layer n. Then, because of this term up here, I always get a delta ik, and let's suppose that for this unit I, that the output is positive, so that g prime is 1, and then you see that you get directly this term, which is just the identity. So this is the direct copy that we had in the forward pass, now as a direct copy in the backward pass. And then of course we have the extra term here, which is this derivative with xk in layer n. Now, as usual in multi-layer networks, in this transition here with two sets of weights, some paths will vanish. There's a bias problem, there's a potential linearity problem. So all the potential problems are here, but in any case, this structure guarantees that some information always goes through directly through these skip connections, through these connections that are also called residual connections. In the AlexNet, it was the designer who said, well, let's do 5.5 convolutions or 3 times 3 convolutions. But how do we come up with these design choices? Can we also turn this around and say, maybe it's better, let's the data decide, and let's just train with giving different possibilities. So here's the previous layer, and then we just offer 1 times 1 convolutions, 3 times 3, 5.5. We can also ask, well, how about pooling? Maybe we need pooling, maybe we don't. So let's also offer as a possibility of a task of this layer 3 times 3 pooling. Now, if you do the parameter count, then you find that if you offer 3 times 3 and 5 times 5, where 5 times 5 in this example here applied on a depth 100 in the previous layer, it really means 5 times 5 times 100, 3 times 3 times 100, 1 times 1 times 100. So this means very heavy computations. This means many, many parameters. And now we can use the trick of orthogonalization, the outer product trick, and do this as follows. We say, I have my total volume, like 100, depth 100 here in this direction. And I separate it out in a pure depth component with index C. K is the index of the filter. And then we have sort of the spatial layout component, the indices X, Y, also for this filter. Now we can think of this outer product also as a convolution where we have 1 times 1 times d. This is the depth part, followed by a 3 times 3 times 1, or a 1 times 1 times d, followed by a 5 times 5 times 1. Now the order, whether you apply the 1 times 1 first or second, doesn't matter if it's linear. For the max pooling layer, it's important that you do it in this specific order. So now the number of parameters is reduced. Now we can offer in that layer many different convolution regions, 3 times 3 or 5 times 5. And this is the idea of the inception module. And if we put this together with a structure of residual connections, we get a very, very complicated network structure, which has in total 60 million parameters. And this was one of the networks that performed very, very well in one of the recent image challenges. Now here's a graph of performance over the years, compared also to the number of operations. And for the more recent networks, the network architecture was in some structures not optimized by hand, but really by reinforcement learning or evolutionary methods on a smaller data set. You first optimize on a smaller but representative data set, and then you reuse the same architectural elements on the full data set of ImageNet. This is called transfer learning. So you reuse some structures, and then once you have found the structure, you retrain. And here's a variant of this transfer learning. In that example, the task was to do face recognition or face verification. And what this group used was the labeled faces on Facebook. Now, users label images that they put on Facebook. 4 million users have labeled images. There were several thousand individuals. And this information was used to train up the big network shown here. But then for the final application, which was a slightly different data set, The convolutional layers were kept, but the final representation layers were retrained. The fully connected representation layers and the labels were retrained on the database that was set up as a challenge. So again, an example of transfer learning. You don't have to retrain all the convolutional layers from scratch. It's in many applications sufficient to use existing filters that have been found on these big ImageNet tasks and just retrain the last 1 or 2 or 3 layers closest to the output. So to summarize, we have a strong inductive bias in the ConvNet structure. Normally, the architectural choices, such as how many layers, such as what region for the convolutions, was done by the users. Nowadays, it's done automatically by the data. The modern structures add more flexibility in the architecture. Then it's the data to decide. But that means we need lots and lots of data. And in the context of the climate crisis, I should also like to mention that these things are extremely energy hungry. It's many, many machines trained for many, many weeks. That's the equivalent of many households over a year. So don't always retrain from scratch. Try to use transfer learning if you are concerned about energy usage. Well, transfer learning is based on the idea that the basic representation in the first few convolutional layers are stable across different imaging tasks, and therefore you only need to train a very few output layers very close to the output for the specific task at hand.